Streaming, am I or am I not? Yeah, I haven't checked. All right, well, let's just assume that I am and such. So, there was something else I had to fix here, and I have forgotten what it is. So, nothing new there. All right, so I guess it's working. So, all right, so anyway, so I guess I might as well just put the video on the screen. So there's this guy called Stephen Young, and he's a physicist, but he's apparently, forsaken all of his physics knowledge and become a flat earther. And it really doesn't make any sense, because I don't think he's a serious flat earther or a serious deny the moon landing and a serious any of that stuff, but apparently, and it's just so, he sort of pulled me in a little bit because I was watching one of his videos and he was just explaining how there's a lot of physics that isn't really tied up and they haven't really made a very good argument defending. And then eventually he got to nuclear bombs, and then he said, there aren't really any nuclear bombs, that they're just conventional bombs. And I'm saying, why the fuck would somebody say that? Who's a physicist? I mean, that's just such an obvious one where, oh yeah, you can tell the difference between a regular bomb and those nuclear ones. Yeah, there's a significant difference. So anyway, I lost all credibility there. But it was just one of these. It's just very disappointing that you can't find. I mean, the point is that I'm saying, oh, maybe this is a guy I could talk to. I could make a video, then he could explain how I'm making a mistake, and in some sort of reasonable manner. And we could get somewhere in terms of having a conversation about the actual evidence for this kind of stuff. Where physics makes a claim, and the fact is the evidence isn't there. And maybe an honest physicist somewhere will admit that yes, they ought to tie this up a little better. They shouldn't be making claims for which there is such a lack of clear, decisive evidence, experimental evidence. And this is like not even complicated stuff. So again, this, I hate to be redundant, but it's all, if we can't get this resolved, there's no resolving anything else. I mean, these are not even difficult questions, and there really should be definitive, hard evidence, really good quality evidence, establishing this crap to be true. All right, let me just fix the properties here so I can do this thing without the focus changing. All right, so I'm going to again draw gravity, just because we're going to use that as it's such a fundamental argument, the understanding of forces and what a constant force would be and how it has to be described. In a sense, you have to be able to explain how it's possible to have a theory of an actual force that does what they claim it does, because what they're claiming it does, it just can't make any sense to anybody reasonable. Okay, I mean, it just, you can't make the reasonable argument explaining it, because it's not reasonable. All right, and so that looks like a pretty good scale drawing of the basic gravitational argument, that you follow this 1 unit of distance, and we'll call this 1 unit of distance 1 unit of time, so it would be 1 second. Is that what I want to do? yeah, I don't know if I want to do that. In 1 second you get 9.8 meters per second. So, and you only travel 4.9. So yes, that is what I want to do. So in 1 second, okay, if I drop something from 4.9 meters, all right, from a height of 4.9 meters, it will fall. It'll hit the ground in 1 second. No matter what its mass is, it'll hit the ground in 1 second. And I would argue that its impact is going to be twice its actual weight. Okay, so when it hits, it's going to be like 10 times its actual weight. Never mind what I just said. Let's not get confused. Just keep it simple. All right. So we know So it's 1 unit of seconds, and then we know the velocity when it hits the ground is 9.8. So those are all established facts. And we know that all of those facts, because this isn't going to matter, the gravity is the same here as it is here, right? 4 feet higher isn't going to make any difference. I mean, 4 meters higher or 10 meters higher isn't going to make any difference. So this experiment will be exactly the same. So it would be 1 second, again, of time. Should emphasize that somehow. That's the time part. And you have the same situation. You'll travel 4.9 meters and you'll be going 9.8 when you hit this location. And your finished velocity will be 19.6. So you do know that this is 1/2 your final velocity, which is quite weird and unusual. That you're going to travel all of this and you're already going half your speed and in 1 second. But the trick is that this is only going to take 1 second too. So this whole thing here will just be 1 second of time. Alright, so you're only going to be in the gravity a total of 2 seconds, and that's why you only have this 19.6. Now their theory is that you're getting units of energy. So in each one of these things that you're traveling, these distances, you're getting a unit of energy. And it's just not being realized as actual velocity. But how can you make sense out of that? Because you're going half your velocity here. So how can you say that, okay, I did these units and I didn't get the same increase in my velocity? So why didn't you get the same increase in your velocity in these units of distance? And how could you get units of distance without getting units of velocity? I mean, once you have this velocity, you're going 9.8 here, then this one must make you go 9.82, right? It's the same distance. So shouldn't this make you go another 9.8? And shouldn't this make you go another 9.8? And shouldn't this make you go another 9.8? When the reality is these two are for free, right? The 9.8 means you get these two 4.9s. These are for both 4.9 meters. 4.9 meters. And you get those two for free. Those are free. You don't have to do any work to get those. You already did the work here. You already have that velocity, so that distance is you're already going to go. And this is the only thing you're getting, which is another unit of 1. So it's 1 unit of time, this whole unit, and you're going to get 1 unit of distance added. So the only added distance is this 4.9 here. And the only added velocity is the whole 9.8 you get for the 1 second, because you're getting it in 1 second units. And it works fine, perfect. So I could say that I can use this same diagram to illustrate any force that we call constant. So if I just said this was wind, you'd have exactly the same circumstance. Now the only difference is that, obviously most winds don't go very fast, so you obviously run out of capacity to increase your velocity pretty quickly, because once you get to 50 miles an hour, it's pretty hard to find a 60 mile an hour wind to push you. But anyway, but I could use a stream. I could use paint spray. I could use photons. Anything I use that I just say, it flows, like a river, okay, and there's a certain amount of it that travels past a certain point. So a certain point, there'll be a certain number, 9.8, for example, and you could just argue that those 9.8 things will hit you, okay, every second. So if you're in this field, that's how many of these things that was going to hit every one of your little atoms. So if I make you big, then you have lots of atoms collecting lots of 9.8. And if I make you small, then you only have a few atoms collecting very little 9.8ers. But you're just going to collect that 9 point. That's how many hit an atom per 1 second. And you can understand it works perfectly. It explains all of this. It works. And the faster I make the force, the more, the more range over which it works in terms of I could go 50 miles an hour, I could go 5,000 miles an hour, I go 50,000 miles an hour, and this would still work with a speed of light force, because the difference between 50 miles an hour and 3 million meters per second is gigantic, obviously. But I mean, how else can you describe this? So this is just like a river, okay? It's just like snowballs you could be throwing. It's just like bits of sand from a sandblaster. Again, paint spray. Any force I apply where it's, spreading at the inverse square law, technically. It doesn't even have to, frankly, to still do this. But it helps to keep everything even. And this is what exactly will happen. And so I, sort of pointed out, you could also just think about this too. You could do this, thing where you could actually have a stream of water, and, you could have a fixed point and then put your bob or boat, okay? And then you could actually give it motion in this direction, and the fact is it will swing back and forth like a pendulum. All right, now obviously water or something else is going to be a lot thicker of a medium. It's going to be a little trickier to be able to move both directions because of the fact that the medium is thick, where gravity's, there's no medium. There's no, and it's also a force that's coming from all directions. So you're also getting hit at these, perpendicular directions by gravity. And so it makes it more even in terms of being able to create a pendulum. But the fact is, you could get that to happen. You could make a pendulum, okay, in the stream, whatever you're using, whether it's paint spray or a sandblaster. You could get something to oscillate in the stream. So it again fits, wind especially. Yeah. So you're just saying, what's the counter argument? I mean, how do you people defend this idea that somehow this 2 units of time, and again it's 9.8 meters per second. I mean, this is Newton, okay, over 1 second. How can you take that formula and turn that into 9.8 meters per second squared? It's 9.8 meters per second over 1 second. That's the real ratio. You get the 9.8 in 1 second units. That was Galileo proved that, and Newton verified that. So why are you claiming or try to imply that it's not in 1 second units by saying second squared? I mean, it's bad enough you're saying second squared, but even just saying seconds, 9.8 meters per seconds would be wrong. It's per 1 second. It's in 1 second units. It's per second. It's 9.8 meters per 1 second of added velocity, and that's clearly what happens. So why are you taking the velocity and assuming there's more to it? Again, this is like this simple argument. I mean, they're basically the people I'm arguing with, this is what they're arguing, is that, I could have two exactly the same masses, and I put one on the scale and then I put the second one on the scale. When I put the first one on, I get 1 unit of weight, and then somehow when I put the second one on, I get 3 units of weight. If I'm going to say it's energy, and if I only get 2 units of weight, how do I have 3 units of energy? How come when I only get this one first compression, it's 1 unit of energy, but second, when you go from 1 on the scale to 2, somehow when going from 0 to 1, it's only 1 unit of energy, but somehow when I go from 1 to 2, it's 3 units of energy. That's what they're arguing. That the first part of the scale is 1 unit of energy, and somehow the next one little unit of distance in the scale is 3 units of energy. I mean, it's the same argument. How can they defend that? What? How do you do that? How do you make that argument that somehow you know, this takes a certain amount of work, and then somehow this is 3 times that work. There's no evidence that it is. There's no evidence that that second pound is 3 times as heavy. There's no way the second pound could produce 3 times anything. It can't. It can only produce the same thing the first pound I put on the scale produced. How can it be possible that just being in second, like I said, if I put this one on first and then put this one on second, now this one adds 3 units of energy. How could it possibly add 3 units of energy? It's the same exact work, same exact action. How could it be 3 units of energy? Yeah, I just, you know, and again, I have to make these arguments for years, and there's nobody, no physicist will respond and just tell me where I said something in here that's completely inaccurate and wrong, where somehow I misdescribed the reality, that this isn't how a constant force works, that all the other forces that could be called constant forces produce exactly the same circumstance. And there's no evidence that twice the velocity is 4 times the capacity to do work. It's just twice the capacity to do work. It only takes twice the energy to make it have twice the velocity. And so that, you know, again, that goes back to the other experiments you can do where you can actually extract some of this knowledge. But I mean, the simplest experiment they should have done is joule type tank experiments. But nobody does those anymore. And you got to wonder why. Why aren't they doing experiments where they convert all the energy into heat and then just measure the heat? And they'll know exactly how much energy something has because they'll extract all of it in the form of heat. Do they believe that's what happens, or do they disagree that that doesn't happen? I mean, why has the joule tank fallen out of favor as a method of displaying or showing or making visible the function?
How is my mouse?
Oh, mouse. Mouse. What the hell is it? I really do have to find a little bit more space to work here. It's just a little bit more. Yeah, so let me see if this video is actually live. Yeah, it is. Okay. Let's see. There's nothing in the way. Okay, so yeah. All right. 3 viewers. Yeah, it's just not good enough. Yeah, I don't. I mean, yeah, I just hate to have to do the same arguments over and over. Hey, what kind of little bug is that? Oh, that's a little free thing of interest, a bug. Yeah, a little tiny bug. Come on, go this way. Go this way. Let's see if we can zoom in on him. Zoom in on the bug. Zooming in on the bug. No, that won't work. Okay. Let's try this. Ooh, this one might work. I don't know if I can get it apart. Let's see. That's a big lens there. I don't see no bug though. Let's see, how far away do I have to put it? Bug, where are you? Yeah, I'm over the bug. Yeah, there he is, but yeah, he's not getting any bigger. Yeah, alright, failure. We'll concede failure. Let's see if that'll work. Yeah, I have lots of broken parts here that I'm working on. All kinds of things. But anyway. So I really can't tell what the hell that is. Obviously it's some sort of fly from my plants that I winter. But apparently I just mortally injured him by shooing him. Yeah, that was too much for him. Anyway, so, hey, somehow I opened another program. Yeah, thank you. I don't want that. Alright, so where were we? Yeah, I'm just doing the rolling argument, but I want to do that. Yeah, the joule tank. So yeah, that was the real argument is then we can get back to this basic argument that Leibniz made. So I'm just going to end up redrawing the one distance and the four distances, and this simple argument that it goes 4 times the distance, but it's only twice the time. So it's only twice the time in the gravity. It's only going twice the velocity. And so why do you think it has 4 times the energy? And to have 4 times the energy, it doesn't have to have 4 times the weight. But yeah, we know it doesn't have 4 times the weight. So yeah, so somehow it's only twice the weight too. And yet you think there's 4 times something here. So the real argument is that the simple truth is the one mass, the 4 mass, all right, going 1 velocity, versus the 1 mass going 4 velocity, okay, and you have this terribly disproportionate result where you're going to claim that this has twice the momentum. It has twice the momentum, and yet, let's see, 16. It almost seems like more than that. It's 4 times. Let me just think. Oh, it's only twice the velocity. Jesus. Yeah, sorry, my bad. So twice the velocity is, yes, it's going to be, this one has twice the momentum. Okay, so 2x the p. Okay, and it has 4 times the kinetic energy, right? Now this one, oh Jesus, Gary, get it right. No, they have the same momentum. Okay, Jesus Christ. All right, and they claim this one has twice the energy. All right, so they have the same momentum. 2 squared is 4 times 1. Okay, yeah, and 4 times 1 is, so that's it. All right, sorry for the confusion. So they both have the same momentum, and yet they claim this one has twice the energy or do 2x the work. So this one will do twice the amount of work with exactly the same momentum as this. Now, how can that be plausible? How can the same momentum do different amounts of work? I mean, how does that logically make any sense? Now, we're not talking about bouncing. We're not talking about elastic, inelastic, any of this kind of crap. We're just talking about, okay, if I take all of the energy of this thing, and I take all of the energy of this thing, so I just drop them in a joule tank, or something like that, and I just convert all of their energy into heat, and I just measure the heat. They're saying there's going to be 2x the heat in here, even though it's exactly the same momentum. And, yeah, I mean, why would people believe that? Let's see, the bug has more integrity than the humans. Yes, it is unfortunate that, he probably was a great thinker compared to the average human. If I could only amplify, somehow his little tiny brain, and make it, give it a little bit of communication skills, he'd probably do so much better than the average human. With that little speck of a brain in there. A little speck of a brain. That's always intrigued me as just one of those facts of life thing that is just so glaring. Was just thinking as a kid. I remember playing with ants. Okay, so this I'm talking about 6 years old, 7 years old, and I would think about the fact that they got little heads and little brains. And I was just thinking about how many ants it would take to make my big giant head, with all my big brain. And it was kind of startling just to say, just to realize how clever these little bugs were, in the sense that I would have to have, I didn't really understand a million, a number that huge, but I mean, I knew it was a huge number of ant brains to duplicate my brain. And I'm like, well, if I amplified all of their knowledge, I should be insanely clever, and I'm not, and so that was my realization was is this big brain thing doesn't mean anything. that obviously I'd much rather have, instead of this human brain, I'd much rather have the spatial, the brains of these tiny bugs, because obviously their brain is hugely more efficient in terms of size and purpose and function than mine. Why have this giant brain if that little bug brain works? So yeah, give me the little bug brain. Give me the same mass, 3 pounds of little bug brain, and I could do amazing things, because look, they got 6 legs, they're controlling antennas, they got to do all the other shit we got to do. Plus they have all kinds of other organs, they're squirting stuff and doing this and doing that. So obviously it's a very sophisticated brain. I just mean, this was always something I found intriguing, was this, and then I realized that the propagandists were telling us that this is about the size of your brain, and then I realized that no, it really isn't about size, it's about functions, and language is a function, and that's the only difference between us and the other mammals, is language. It's not about the size, it's about the organs and the function and what they're devoted to, how they're organized through the operating system. That's what decides. Let's see, maybe it takes 4 times the work. See, lifting is just silly because you don't lift at the free fall rate. Okay? See, free fall is a very specific speed. It's not this speed, it's not that speed, it's not any speed. Very specific. Okay? You do this 4.9 meters in 1 second. That's the actual distance you travel in your, when you get your 1 second of gravity, this is all you get, is 4.9 meters. So it's, you have 9.8 meters of velocity, but you only got 4.9 meters of actual new velocity. All right, so it's something to always recognize. But that's the free fall speed. If you go a different speed in gravity, you're not going to be in it 1 second anymore. So that's the key thing. If you're in it more than 1 second, guess what? More force is going to hit your sail, more wind. If you're in the wind longer than 1 second, you're going to collect more wind, right? You're in the wind less than 1 second, well, then you're going to have less than that 4.9. So that has to be understood, that you can't talk about how fast you lift. So if I lift this, taking 1 day to lift it, I will do 40,673 joules of work. I mean, it'll be real energy, just holding it the whole time and incrementally moving it. It'll be real work, and I'll add up a huge bill. But if I do it, if I put it somewhere quickly, okay, no, not so much work. Now, obviously, if I go quicker than the free fall speed, then I went faster than I need, and I have to actually slow down. But if I actually throw it at the free fall, at the rate it hits the ground at free fall, if I throw it at that velocity, it'll be perfectly efficient and it'll go right back up on its shelf. And so I'll be perfectly efficient. But that's the only speed that's perfectly efficient. And every other speed, okay, it can get you there sooner and you'll do less work, but if you have to put on the brakes, you can sort of understand, if you have to put on the brakes, then you've put too much fuel in the tank, so to speak. You've wasted fuel if you have to use the brakes. But thank you for pointing that statement out, because it just gave me the opportunity to explain all that. So I'll read it once more. Maybe it takes 4 times the work to lift a brick 4 times as high. Did you ever think of that? Well, that's just ridiculous. So I'm just saying that if you lift it at the free fall speed, the same speed it falls at, it's only twice the velocity. Again, you need to just have twice the velocity to go 4 times higher in gravity. So twice the velocity does the trick. But then when you release it, you only reaches twice the velocity. Well, it's all you need to go 4 times as high. Twice the velocity will make something go 4 times higher than 1 unit of velocity. Okay, so as the drawing sort of shows, 1 velocity gets you this height. 2 velocities get you this height. And it doesn't matter what your mass is. That's not true. Just think for a minute. Relative, as long as your mass doesn't change between the 2 experiments, of course. because you will have to put more energy in, but the velocity won't matter. So the simple point is, same mass, and you just double the velocity, you'll get 4 times as high in gravity. All right, so you're wrong about releasing it at twice the velocity. Is that really so complicated? So you're talking like you know better, fucktard. Do you think you got the right answer so far? I mean, you know, you're the one assuming it's going 4 times faster when it's not. Okay, free fall, 4 times the distance, it's twice the time. Twice the time, well established fact. Twice the velocity, well established fact. Anyway, so let's see. But keep talking about the time when you're burning ants with a magnifying glass. So I don't know what that has to do with this subject, but I have to admit I did do that. Okay, as a kid, magnifying glasses in Louisiana, lots of stuff you can have fun with. I melted lots of things. Yeah. Next to magnets, magnifying glasses were one of my favorite toys. And one my parents did everything they could to keep out of my availability. All right, so it isn't disappointing. So what is it? You're gonna say anything else, fuckhead? I mean, you did your little arrogant crap, you know, making it seem like I'm the dope because it's not so complicated. It's so simple. It's so simple. You know, somehow it's going half its velocity here. I mean, that's so obviously sensible. I mean, yes, why wouldn't it go half the velocity 1/4 of the trip? I mean, of course it's a time dependent. I mean, it's a constant force, yet you get half your velocity in the first little chunk of distance you travel. So you're constantly getting it over the same distance. You get the same amount of force somehow. Yet, when you get that first unit of distance, you're going half your velocity. And the other 3 units of distance only give you 1 more half. That's all you get. So 1 unit of distance gives you half your velocity, and then it takes 3 units of distance to give you your second half of your velocity. That's not complicated. That's so simple and so obvious that makes perfectly good sense. That, yes, of course, you're getting it in units of distance. What else could possibly be true? Yeah, fuck you. God, this planet is shitheads. But I mean, realistically, is it asking too much that somebody could just draw this stuff and then explain where I said something incorrect? Where somewhere in this drawing it's fundamentally deceptive and wrong about what actually happens? Of course they can't. See, they actually think it's the same work. You know, me lifting something really slowly is the same work as me lifting it quickly. That I can't change how much work it is to move something from here to here. When in every circumstance, with any other constant force, of course I can move things quicker and, you know, save a huge amount of energy. So I've used the stream example. You're just going to cross a stream flowing that way. Obviously, the faster you get across the stream, the less you're going to be pushed downstream, and the less work you'll have to do to correct for your damage done to your travel. And likewise, even if you're going with the stream or you're going against the stream, it's all about time. The faster you get upstream, the faster as you defeat the current, the less work you're going to have to do. And the slower you're fighting the current, the longer you're fighting it, the more work you're going to have to do. And that's just a simple fact. There might as well just count them as little blobs of stuff, and you're just saying you have to, the sooner you get out of the stream, the less work you're going to have to do. And the longer you're in the stream fighting against those bits, the more work you're going to do. Now, obviously, if you're going downstream, right, the faster you go, the less you're going to get pushed. Obviously. Because you're still in it less time, and you're going the same direction as the stream's going. But see, in gravity, it wouldn't matter because, it's 3 million meters per second versus 50 meters per second. Obviously, that differential isn't going to create any kind of big difference. But it's just an absolute fact. I mean, you could just do this over and over again, keep explaining how it's a time-dependent force. I mean, and again, I shouldn't even have to say it. I mean, everybody should know this. This is what Newton said. I guess they, when I was a kid, they were still writing 9.8 under 1 second. I mean, over 1 second. So, I mean, you still had that vision of the ratio. I mean, they didn't just do this 9.8 meters per second squared thing. They actually showed you a fraction. So you actually got the idea of understanding that it's per 1 second units. And it just absolutely is the truth. And so, I guess I had that advantage that even though some of these people would say that 9.8 meters per second squared thing, you didn't see it written that way. All right, let's see what this guy said. The speed with which it is lifted is irrelevant. Well, I'm telling you, it obviously isn't irrelevant, okay? Spaceships take advantage of getting into space quickly. If they didn't, they would never get into space. So they have to get there quickly. They have to defeat the gravity. They have to get through it quickly. So you're just an idiot, a moron, an imbecile, a fool. Also, muscles. Well, let's not talk about muscles. It's irrelevant. Let's just come up with some other mechanism to lift and move things, okay? And quit playing games that somehow moving this slowly has something to do with muscles. No, it just has to do with the fact that the whole time you have to suspend it. You have to do the holding. It's not on a steel girder, okay? And you're not just doing, here, I slid it onto the higher girder, and then I slid it onto a higher girder. We're just talking about you having to actually do the work of holding it, suspending it against gravity. You're absorbing the 9.8 meters per second. All right. So you're just such a cheater. It requires a constant input energy to contract, regardless of whether or not they're doing any work. I said work, not energy expenditure. I don't care. Okay? I mean, you want to play a game that there's something called work that means something. No, it's just energy expenditure. You want to think, what's work then? Work is energy expenditure. It's the consumption of it. That's how, you can't have a conservation rule without talking about work being essentially what you started with, which is force. You can't, you can't pretend to have anything called conservation if you're going to pretend that work isn't completely describable as the same thing as force. How can you make a separation? You're supposed to conserve it. And you even say you do. So in like the ballistic pendulum, for example, when you lose 99.94% of your kinetic energy, you don't say you lose it. You say it's in the pendulum. You're saying it's red hot in there. Okay? There's thousands of joules of energy in there, but you'll never measure any of it because you're all lying scum. But anyway... So anyway, let me just read that again. So he says, the speed with which it is lifted is irrelevant. So it's just absolutely silly. And again, it doesn't have anything to do with facts. So this is just an absolute fact. If I have a gravitational body and I'm going to go from point A to point B, or from point B to point A in this case, of course it matters how fast I go. That's all that matters. The faster I go from point A to point B, the less the gravity is going to pull me in. Just an absolute fact. The less I'm going to have to fight the pull of the gravity. The less gravity will actually be absorbed by me. I will gain less of this vector the faster I'm going. So the faster I'm going, the less of that vector I collect. Quite obviously, it matters. And the same is true when I'm traveling. MGH doesn't work when I'm heading into a body. So if I start with a speed of 100 miles an hour here, you can't use this distance, h, all right, to calculate how much extra velocity I'll get. Because I'm already moving and I'm going to go through the gravity much quicker. And it is, in fact, a time-dependent force, and you can't change that. If I'm only in this... If Without this 100 miles an hour, if this would have, like if I just placed the object here, and it would have taken 4 seconds for it to get here, right? But because of this 100 miles an hour, it's only going to take 2 seconds. Obviously, that difference in time means I'm going to get pushed more, okay, by the gravity when I don't have the head start. And I'm going to get pushed less by the gravity when I have the head start. I mean, obviously the head start's going to mean I'm way ahead speed-wise anyway, so I'm going to be going much faster when I reach the planet, but MGH won't give you a right answer. If you use MGH, you're going to get the wrong answer. Dead absolute fact. Okay, use MGT, you're going to get the right answer because gravity is a time-dependent force. All right, so I don't think he said anything else. Also, muscles require a constant input of energy to contract regardless of whether or not they're doing any work. So the fact is you could just argue it's work just holding something. So I'm not going to argue the point. And clearly the argument is the longer you're holding it, the more work you're going to do. So we're talking about a system that has to balance, do the actual work. Like applying a force to an object, whether you move the object or not, you're applying the force, you're doing work because you're pushing, all right, in, and it's pushing back. So it's work whether it moves or doesn't move. Let's see. In that case, because what you understand is that your flesh is what's moving. Your flesh is doing just like your ass when you're sitting is doing the work. That's why it gets tired. It's because it's actually working. It's constantly rebalancing your condition. But again, it just makes it more complicated to start getting into human biological dynamics and just stay with some kind of physical system. Like a pulley and an electric motor and gears. You could just have 500 gears and you're pulling something very slowly up. All right, the fact is you're going to do a lot more work, okay, the slower you lift it. Those pulleys will do more work. The system will do more work. And that's, again, this was proven back in Joules' day. They did do these experiments. So let's understand they actually did do these experiments. And that's exactly what they found is you drop something twice as slow. And the only way you can drop it twice as slow is to have some mechanism where it's twice, the thing you're pushing is twice as heavy or some other mechanism. Or you're dropping it twice the distance. And that's what they found. Twice the distance made twice... you ended up with twice the energy. But you're not going, again, you're not going the speed of gravity. Gravity is a very specific speed. It's a very time-dependent speed. You move some other speed, it's a different amount of force. The force is in timed units. How many times do you have to... I mean, really. You people are all defending some notion that it's really not 9.8 meters per second of added velocity, change in velocity, over 1 second. You're saying this isn't true. That's Newton, okay? That's Galileo. You're saying that isn't true. I mean, Newton made it really clear. I read the paragraph in a couple of videos ago. And there's the word time about 7 times in the paragraph where he's describing how gravity functions. It's in units of time. It's a time-dependent force. So what was I going to illustrate? Oh, shit. Oh, yeah, Joule. So what they do is Joule tank, or they do this silly experiment, right, where they have a pulley and then they drop a weight. Okay. Now, the problem with this experiment, right, is I guess it's just pretty much a friction experiment again. But they're assuming that this drop height is always the same amount of gravitational energy collected. So no matter how slowly I make this weight fall, it's the same energy. When, of course, it's not the same energy. So when I make this mass big, right, if I make this mass, high, big mass. Obviously this drops much slower, which means there's much more energy going to be collected in the mass. All right, so I'll be able to get this up to a higher velocity, but it's going to be much lower than a lighter cart's velocity. So this drops much slower. The cart ends up with much more energy. So I did the same experiment, but this dropped much slower, and I have a lot more momentum in the cart. So in the case of the heavy cart, I'm going to have maybe 100 momentum, and then I could have a light cart, okay, that was, 1/10 the mass, and this will fall super fast, right? It'll be out of the gravity so fast, 10 times faster, because it's so light. So it's just going to go boom. And this is going to have a tiny momentum by comparison, 10% of the momentum. Because it is a time-dependent force. If we allow the mass to fall fast, it'll just collect the gravitational, the gravitational minimum. And if you let it fall slow, then it'll keep increasing how much energy it can collect. It'll collect more and more and more and more because it's taking longer and longer and longer to fall. Yeah. Should be obvious to everybody. Should be. But I just can't believe that this really does come down to all you people. You really don't believe this is the accurate formulation for gravity. You really don't think it's 9.8 meters per second of increase in velocity per 1 second units. You don't think that's true. When it's just so frickin' elemental to the whole point. It's just what gravity is. It's the definition of it. Is that 1 second thing. That 1 second thing is the definition. That makes this force. That makes this fraction mean something. Doesn't mean anything without that 1 second there. Alright, so now we'll do the thin ice argument. The rolling. Again, it's just so clear, and the fact is, like I said, until I get it, somebody can make some sort of reasonable argument, and they just can't, and that's just the truth. And so there's never going to be a reasonable explanation for how this illusion, okay, and that's all it is. All right, well, I got a little too much line here. Okay, erase a little bit. Okay, so the ball's going to end up here, stopped here. And this one's going to end up stopped here. All right, now, so obviously this is going to be 1 velocity. This will be 2 velocity. Same mass. All right, there's just no way to not understand exactly what's going to take place here, right? I have twice the velocity. It's going to go across this surface faster. And so as it's going across the surface, gravity's pushing down this way. It's not pushing down the same amount per unit of distance. Because you can understand it's like even if it was rain and I'm collecting it in a bucket and I'm moving this way, I'm going to collect it, but I'm going to collect it in units of time. I'm not going to collect it in any other units. It's all I can do is collect it in units of time. So if it was a river or a stream, it's how fast am I going across the stream with the bucket pointed collecting the water, the hose collecting the water. That's all there is. There can't be any other way to understand it. So this experiment is exactly this experiment right here. So again, you're going half your speed here. Okay, you know that. This experiment is this experiment. There's no way around it. And this is going to be 1 unit of time. So this is 1 unit of time. This is 1 unit of time. And this whole thing is 1 unit of time. So again, you've proven the point. It's 4 units of distance, but it's only 2 units of time. And it's just so clear. You're going half your velocity here. It means you only lost half your velocity going across this distance, which means this was 1/3 the friction. It's 1/3 the weight per inch. That's why you can slide across thin ice. So you can slide fast across thin ice and not fall through the ice, because how much you weigh per inch, okay, per unit of distance is less, and it gets, how much you weigh, you get heavier and heavier as you slow down. So over this period you weighed exactly the same as you weighed here. You collected let's say it was 9.8 rocks per second. You collected 9.8 rocks over this whole distance, and then it was 9.8 rocks here. And you know that's all it is. So you know that you got just as much weight on this small surface as you have weight across this huge surface. Same number of rocks you're placing on the surface. Same number of rocks, and you know that obviously if it was thin ice, this won't break. This will break. It's easy to understand. Again, I have to do this for 10 years, and no one's gonna rationally explain to me where I said something wrong here, that this isn't what happens. So I mean, their argument is, again, let's just understand, they're saying they're 1 unit of heat here. So in this 1 second you got 1 unit of heat, right? And then here they're saying you got 3 units in the ground here. You got 3 units of heat. So three heats. Okay, if we could do the experiment. So somehow I got 4 times the energy locked up in here. So even though it was 1/3 the friction, right? It's 1/3 the weight per inch, 1/3 the rubbing friction, and yet I collected 3 times the heat. Come on, I made 3 times the heat. So I reduced the friction by 3 times, and yet by reducing the friction 3 times I gained 3 units of extra heat. I made 3 units of extra heat. Everybody knows that isn't true. I mean, everybody who's honest and fair and reasonable will say, yes, okay, I get it, that can't be true. It's twice the heat here there is here. Twice the velocity, twice the heat, twice the energy, twice the force. Because again, I can't possibly make a rational argument that there's some difference between putting this mass on the scale and putting this mass on the scale. One of them can't be 1 energy, and the other one can't be 3 energies. That is nonsense. All right. Yeah. So I'll give you a minute or two to see if anybody responds with anything, and maybe I'll just call that a video and just say, yes, there's no communication with the human race. It's just so depressing. I mean, all these people with opinions, and not any of them have the integrity to just make the video I just made. Do the drawings, explain how it's 9.8 something else here, not per second. Explain how it's a distant dependent force by explaining how it actually works. Draw it. What's the big deal? Why is drawing it a hard thing for you to do? Draw it. Explain how this is 3 times the friction. Here. Yeah, explain that. Explain how it weighs just as much per inch, that the surface feels the same weight. When, again, all these people know this, right? They know that if they took a car and they moved it fast enough, they could have an actual person in the road, dug in under the asphalt, right on the surface of the asphalt. And if they ran the car fast enough, the person would survive. They wouldn't be crushed by the wheel of the car because the wheel wouldn't be on top of them long enough. Fact. Now, the back wheel spinning might be a problem, but, we're saying they're coasting at, say, 100 miles an hour. Fact is, those experiments you could do. I'm sure somebody somewhere has already done some kind of dopey experiment like that, because it's just a fact that you can defeat the gravity by getting through it quickly. Absolute fact. It's so demonstrable, it's so obvious this is how it works. The faster you're going, the less friction there is. The slower you're going, the more time the river has to push you into some surface. The wind. If it was a blowing wind, the more time you give the wind to push, the more you're going to be pushing, the more force you'll have to push. All right. So I guess I'll call it a video. Yeah, I just need something better to interact with. It just isn't, and the opposing argument can't be made in any kind of reasonable, fair form. And it's just disappointing. And like I said, I was really... I spent an hour listening to this guy, and he doesn't punchline you right from the start. So he doesn't say right from the beginning, I've turned into a complete religious, spiritual loop-de-doo, okay, and that's why I'm rejecting physics. And so it all sounds so freaking rational. And although I disagree with him, right? I mean, he's basically saying the particle part of physics is the wrong part, and he's all like gooey about ether and waves. But yeah, it turns into complete. He loses all credibility as soon as he starts saying things like nuclear bombs aren't a thing. I mean, it's just ridiculous. And he's claiming nuclear bombs aren't a thing because he can't accept the existence of atoms. And somehow that's an obnoxious theory that there's atoms. I mean, it's so ridiculous. I mean, even if you want to just turn atoms into... I mean, atoms aren't like the original word atom, where you're saying the atom is indestructible. Obviously, when we say atom, we're not talking about something you can't reduce to an electron and a proton. So it's not even like he's rejecting that, and that's what he should be talking about. He shouldn't be talking about atomism. He should be talking about electron and protonism, because that's the real particle threat. That's the thing. Isolating electrons and protons, isolating the elements of charge and magnetism, that was the death of ether. Okay, it's once you have charges, yeah, you're done. You're done making those out of ether, and now you have to have some mechanism that just pushes them around, which I of course have already explained all of that, so I won't bother doing that in this video. But anyway, just very disappointing. So the good news is they don't get any traction. So he was doing a video on some bitch's channel, some doctor, some medical doctor who's a loop-de-doo. And you're just like, these anti-vaxxers, whatever these people are, these anti-ers, and it's just, they just ruin dissonancy because they take it to these idiotic, moronic extremes. Because there's this much corruption, then they just make up a fake story about this other 90% more corruption, and there's enough corruption that's real to argue. Why do you have to make up fake corruptions and fake shit to argue? Just argue the real shit. All of that's very disappointing too. Fuck. Alright, so I guess I will go. Let's see, 5 people. Well, there was something anyway, but yeah, it's just too few. Too little interaction. I mean, I get tired of soapboxing. I mean, if I can't solve this, like I said, if we can't resolve this, 9.8 meters per 1 second, if we can't settle that gravity is a time-dependent force, there's just no way around it. That's what it does. That's what there's no other way to describe a constant force except to describe it as time-dependent. So if somebody can please describe to me how a constant force could be anything other than time-dependent. Yeah, there's just no other way to describe it. Because you can't get away with saying, well, okay, it gains the same energy per distance because it's acquiring velocity. So we know that doesn't work. It doesn't acquire velocity consistent with distance. So it just doesn't make any sense. How can it be acquiring energy consistent with distance but not velocity consistent with distance? It makes no sense at all. How can, it's so obvious that being pushed twice as much means you're going to be going twice as fast. Again, it's just so obvious that 1 unit of energy and do exactly the same thing. You can't make 3 units of energy doing exactly the same thing. If the action only creates 1 unit of energy, you can't make the same action create 3. Can't do it. It's not reasonable, people. Alright. But yeah, it's just... Damn. I just never thought this would be the problem. Trying to get somebody to argue with me in a reasonable manner. Prove me wrong. And they won't prove me wrong. They'll just assert I'm wrong. These are not complicated drawings. Draw them. And show how I'm wrong. Fuck. Alright, yeah, that's all I can do. So, anyway, till the next time and such, and so forth and whatnot. I guess we're done. Yeah, I guess I'll end this way.